mathematicians for thousands of years, he wants to publish it. Unlike his peers, Cardano has no need to keep the solution a secret. He makes his living not as a mathematician, but as a physician and famous intellectual. For him, the credit is more valuable than the secret. The only problem is the oath he swore to Tartaglia, who won't let him break it. And you might think this would be the end of it. But in 1542, Cardano travels to Bologna, and there he visits a mathematician who just happens to be the son-in-law of one Scipione del Ferro, the man who, on his deathbed, gave the solution to the depressed cubic to Antonio Fiore. Cardano finds this solution in Del Ferro's old notebook, which is shared with him during the visit. This solution predates Tartaglia's by decades. So now, as Cardano sees it, he can publish the full solution to the cubic without violating his oath to Tartaglia. 3 years later, Cardano publishes Ars Magna, the Great Art, an updated compendium of mathematics. Written in 5 years, may it last for 500. Cardano writes a chapter with a unique geometric proof for each of the 13 arrangements of the cubic equation. Although he acknowledges the contributions of Tartaglia, Del Ferro, and Fiore, Tartaglia is displeased, to say the least. He writes insulting letters to Cardano and CCs a good fraction of the mathematics community. And he has a point. To this day, the general solution to the cubic is often called Cardano's method. But Ars Magna is a phenomenal achievement. It pushes geometrical reasoning to its very breaking point, literally. While Cardano is writing Ars Magna, he comes across some cubic equations that can't easily be solved in the usual way, like x cubed equals 15x plus 4. Plugging this into the algorithm yields a solution that contains the square roots of negative numbers. Cardano asks Tartaglia about the case, but he evades and implies Cardano is just not clever enough to use his formula properly. The reality is, Tartaglia has no idea what to do either. Cardano walks back through the geometric derivation of a similar problem to see exactly what goes wrong. While the 3D cube slicing and rearrangement works just fine, the final quadratic completing the square step leads to a geometric paradox. Cardano finds part of a square that must have an area of 30, but also sides of length 5. Since the full square has an area of 25, to complete the square, Cardano has to somehow add negative area. That is where the square roots of negatives come from, the idea of negative area. Now, this isn't the first time square roots of negatives show up in mathematics. In fact, earlier in Ars Magna is this problem. Find two numbers that add to 10 and multiply to 40. You can combine these equations into the quadratic x squared plus 40 equals 10x. But if you plug this into the quadratic formula, the solutions contain the square roots of negatives. The obvious conclusion is that a solution doesn't exist, which you can verify by looking at the original problem. There are no two real numbers which add to 10 and multiply to 40. So mathematicians understood square roots of negative numbers were math's way of telling you there is no solution. But this cubic equation is different. With a little guessing and checking, you can find that x equals 4 is a solution. So why doesn't the approach that works for all other cubics find the perfectly reasonable solution to this one? Unable to see a way forward, Cardano avoids this case in Ars Magna, saying the idea of the square root of negatives is as subtle as it is useless. But around 10 years later, the Italian engineer Raphael Bombelli picks up where Cardano left off. Undeterred by the square roots of negatives and the impossible geometry they imply, he wants to find a way through the mess to the solution. Observing that the square root of a negative cannot be called either positive or negative, he lets it be its own new type of number. Bombelli assumes the two terms in Cardano's solution can be represented as some combination of an ordinary number and this new type of number, which involves the square root of -1. And this way, Bombelli figures out that the two cube roots in Cardano's equation are equivalent to 2 plus or minus the square root of -1. So when he takes the final step and adds them together, these square roots cancel out, leaving the correct answer 4. This feels nothing short of miraculous. Cardano's method does work, but you have to abandon the geometric proof that generated it in the first place. Negative areas, which make no sense in reality, must exist as an intermediate step on the way to the solution. Over the next 100 years, modern mathematics takes shape. In the 1600s, François Viet introduces the modern symbolic notation for algebra, ending the millennia-long tradition of math problems as drawings and wordy descriptions. Geometry is no longer the source of truth. René Descartes makes heavy use of the square roots of negatives, popularizing them as a result. And while he recognizes their utility, he calls them imaginary numbers, a name that sticks, which is why Euler later introduces the letter I to represent the square root of -1. When combined with regular numbers, they form complex numbers. The cubic led to the invention of these new numbers and liberated algebra from geometry. By letting go of what seems like the best description of reality, the geometry you can see and touch, you get a much more powerful and complete mathematics that can solve real problems. And it turns out, the cubic is just the beginning. In 1925, Erwin Schrödinger is searching for a wave equation that governs the behavior of quantum particles, building on de Broglie's insight that matter consists of waves. He comes up with one of the most important and famous equations in all of physics, the Schrödinger equation. And featured prominently within it is I, the square root of -1. While mathematicians have grown accustomed to imaginary numbers, physicists have not and are uncomfortable seeing it show up in such a fundamental theory. Schrödinger himself writes, "What is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. The wave function psi is surely fundamentally a real function. This seems like a fair objection, so why does an imaginary number that first appeared in the solution to the cubic turn up in fundamental physics? Well, it's because of some unique properties of imaginary numbers. Imaginary numbers exist on a dimension perpendicular to the real number line. Together, they form the complex plane. Watch what happens when we repeatedly multiply by I. Starting with 1, 1 times I is I times I is -1, by definition. -1 times I is -I, and -I times I is 1. We've come back to where we started, and if we keep multiplying by I, the point will keep rotating around. So when you're multiplying by I, what you're really doing is rotating by 90 degrees in a complex plane. Now, there is a function that repeatedly multiplies by I as you go down the x-axis, and that is e to the ix. It creates a spiral by essentially spreading out these rotations all along the x-axis. If you look at the real part of this spiral, it's a cosine wave. And if you look at the imaginary part, it's a sine wave. The two quintessential functions that describe waves are both contained in e to the ix. So when Schrödinger goes to write down a wave equation, he naturally assumes that the solutions to his equation will look something like e to the ix, specifically e to the ikx minus omega t. You might wonder why he would use that formulation and not just a simple sine wave, but the exponential has some useful properties. If you take the derivative with respect to position or time, that derivative is proportional to the original function itself. And that's not true if you use the sine function, whose derivative is cosine. Plus, since the Schrödinger equation is linear, you can add together an arbitrary number of solutions of this form, creating any sort of wave shape you like, and it too will be a solution to Schrödinger's equation. The physicist Freeman Dyson later writes, "Schrödinger put the square root of -1 into the equation, and suddenly it made sense. Suddenly, it became a wave equation instead of a heat conduction equation. And Schrödinger found, to his delight, that the equation has solutions corresponding to the quantized orbits in the Bohr model of the atom. It turns out that the Schrödinger equation describes correctly everything we know about the behavior of atoms. It is the basis of all of chemistry and most of physics. And that square root of -1 means that nature works with complex numbers and not with real numbers." This discovery came as a complete surprise to Schrödinger as well as to everybody else. So imaginary numbers, discovered as a quirky intermediate step on the way to solving the cubic, turn out to be fundamental to our description of reality. Only by giving up math's connection to reality could it guide us to a deeper truth about the way the universe works. Not gonna lie, I learned a ton while making this video, because I really had to engage with some ideas that I was already familiar with. And that is exactly what happens with Brilliant, the sponsor of this video. Brilliant is a website and app that teaches you all kinds of STEM concepts, from geometry to quantum mechanics, and you learn by doing. They use interactivity to bring your understanding to the next level. Like calculus? No problem. It's way more fun when you work through the material yourself and get to manipulate it visually. Check out these surfaces of revolution, a clear demonstration of how you can use an integral to find volume. The problems are carefully curated to increase in difficulty as you go, and if you get stuck, there is always a helpful hint. If this video has whetted your appetite for complex numbers, they have an awesome course on that subject, from the Mandelbrot set to Euler's formula. And for viewers of this channel, Brilliant is offering 20% off an annual subscription to the first 200 people to sign up. Just go to brilliant.org/Veritasium.